Here we will continue our discussion of weak acid-base pH by taking a look at polyprotic acids. So as we've looked at acids so far, and when we looked at our proton transfer, we've been dealing with transferring a single hydrogen. But we can have compounds that can have more than one acidic hydrogen. An example of that would be something like carbonic acid, H2CO3. This is what we describe as being a diprotic acid. It's diprotic because it has two hydrogens, both of which are acidic. If we have only one acidic hydrogen, we're going to call that monoprotic. If we've got two, diprotic, three would be triprotic. So the carbonic acid, it's a diprotic acid because it has two acidic hydrogens. When we lose those hydrogens, they still get transferred one hydrogen at a time, which means that our dissociation is going to take place in multiple steps. So in the case of a diprotic acid, it's going to take place in two steps. So in the first step, we would have H2CO3 losing one hydrogen, becoming HCO3 minus and producing hydronium. It is this HCO3 minus that still has that acidic hydrogen that is dissociating in step 2. Each step is an equilibrium. So each step is represented by an equilibrium expression. It has a corresponding K value. Notice if we compare the K for step 1 to step 2, the K for step 2 is significantly smaller than the K for step 1. The fact that the K for step 1 is, or for step 2 is much smaller, that's going to indicate that out of these two steps, we're going to get more dissociation coming from step 1. So step 1 will always have our greater percent dissociation. So since each of these is occurring in multiple steps, each step's going to generate its own equilibrium with its own equilibrium concentration. And we would take a look at each of these steps individually. So if we were to take a look at step 1, so we're looking at problem number 7 on our worksheet. If we're taking a look at step 1, we want to determine the concentration of all species present if our initial concentration is 0.2 molar. And so we're going to take the dissociation step for step 1, so our H2CO3 plus water, producing the HCO3 minus and hydronium. So we're going to set up our ice table just like any of our other problems where we're finding equilibrium concentrations. So we plug in our initial concentration of 0.2 molar. We don't care about our water, and our products here are initially 0. As we proceed towards equilibrium, my reactant will go down by X, my products will go up by X. So at equilibrium, I'm going to have 0.2 minus X for my acid, X for my HCO3 minus, and X for my hydronium. So we would plug this into our K expression, which we had on a previous slide. So we plug in X for the bicarbonate and X for hydronium. X times X gives me X squared divided by my acid of 0.2 minus X. And that equals the K, and this is the K for step 1. And we were told K for step 1 was 4.3 times 10 to the negative 7th. So just like any other equilibrium problem, we're going to want to take this and we're going to rearrange and we're going to solve for X. In doing so, remember that we've got small k's here. So if K is small, we're going to check for X's negligibility. Remember, we're going to do that by taking K divided by I If it's less than or equal to 10 to the negative third, x is negligible. And in this case, we would find that x is negligible. So that negligible x allows me to take this minus x and cancel it. So that my equation becomes x squared over 0.2 equals 4.3 times 10 to the negative 7th. So we're rearranging to solve for x. So I'm going to have 4.3 times 10 to the negative 7th times my 0.2. Take the square root of both sides, and we'll get that our x is 2.9 times 10 to the negative 4th. So the question is asking us for concentrations of each species. So my H2CO3, so we plug our x back into our ice table. If we subtract that 2.9 times 10 to the negative 4th from 0.200, we round back to our appropriate significant figures. We're still going to have 0.2 molar for my original acid. My HCO3 minus is going to be 2.9 times 10 to the negative 4th molar. And my hydronium is 2.9 times 10 to the negative 4th molar. So from that initial dissociation, I get these concentrations of my ions. Now we're also asked to calculate the percent dissociated. So our percent dissociation is our change. So our change is x divided by our initial concentration, which is going to give me 0.145%. So this is the dissociation for step 1. Now, this dissociates in 2 steps, and we said that in the second step, it is going to be my HCO3 minus that is further dissociating. So in our next problem, number 8, we're going to be asked to take step 2 and determine the equilibrium concentrations from that step. So step 2, it's the HCO3 minus dissociating. Giving us hydronium and CO3 2 minus. Now here our ice table gets a little bit different. When we go to set this up, my HCO3 minus, remember it's coming from step 1. So we're not plugging in that initial 0.2 molar concentration. That's the concentration of the original acid. This gets formed in step 1, so we need the concentration of it from step 1, which was 2.9 times 10 to the negative 4th molar. So we're plugging in the concentration from step 1 because that's where we're forming this. This can't dissociate until that's formed, and so that's the concentration we're basing it on. Now, we don't care about our water. The other different thing here is going to be that I have an initial concentration of hydronium. Step 1, we generated 2.9 times 10 to the negative 4th molar of that hydronium. So I'm going to plug that in as my initial concentration of my hydronium. And then we don't have any carbonate yet. So this is where we're different from our previous ice tables, is that we have an initial concentration of one of our products. Now we set up the rest of our ice table as usual. So my reactant goes down by x. My products each go up by x. So at equilibrium, my HCO3 minus is 2.9 times 10 to the negative 4th minus x. My hydronium is 2.9 times 10 to the negative 4th plus x, and then my CO3 2 minus is x. So we go and plug this into our K expression for step 2. So K says we're going to have the concentration of our carbonate, which is X, times the concentration of our hydronium, which is 2.9 times 10 to the negative fourth plus X. And then that's divided by my HCO3 minus, which is 2.9 times 10 to the negative fourth minus X. And that's equal to my K. This is the K for step 2, which we're told is 5.6 times 10 to the negative 11th. Again, we're going to check to see if X is negligible, and we're going to find that it is. So X being negligible, when we've seen that before, we said it allowed us to get rid of any minus X. It's also going to allow us to get rid of any plus X. So if I get rid of my plus X and my minus X, I've got 2.9 times 10 to the negative fourth X on top. I have 2.9 times 10 to the negative fourth on the bottom. Those cancel, and this just becomes X equals 5.6 times 10 to the negative 11th. Always, we take that X and plug it back into our ice table. So plugging it back in, my HCO3 minus, I round back to my appropriate significant figures, and I'm going to have 2.9 times 10 to the negative fourth. My hydronium, again, I can add X to this. I round to my appropriate significant figures, and you can double check this on your calculator. 2.9 times 10 to the negative fourth molar. And then my CO3 2 minus is 5.6 times 10 to the negative 11th molar. When we have these polyprotic acids, we get a very complex solution. So we've got initial H2CO3, which we said was still going to be 0.2 molar. We have HCO3 minus, which is 2.9 times 10 to the negative fourth. We have CO3 2 minus, which is 5.6 times 10 to the negative 11th. And then we have hydronium, which was 2.9 times 10 to the negative fourth. So we've got all 4 of these species present in that solution, resulting from dissociation by 2 steps. Now we said our greatest dissociation was taking place in step 1. We calculate our percent dissociation here. It's our change of 5.6 times 10 to the negative 11th divided by our initial of 2.9 times 10 to the negative 4th, which is going to give me 1.9 times 10 to the negative 5th percent. So very small percentage here, but it is producing additional substances in solution. Now, from both steps, and we always want to consider both steps because some of these acids are going to be stronger than others, generating more hydronium, and so they may have an impact from that second step. But from both steps, our hydronium concentration is 2.9 times 10 to the negative 4th. Our pH for polyprotic acid is going to be the pH after all dissociation. So our pH is going to be the negative log of this equilibrium concentration, which is going to be 3.54. So problem number 10 is going to give you another polyprotic acid. You've got an H2SO3, so you've got a diprotic acid. You can have dissociation in 2 steps. Problem 10 will give you guys additional practice with this. You will have an answer key on Blackboard that you can check your work to problem number 10.